Welcome back to College Algebra, Math 1313. Today we're going to be talking about domain and range and how that affects functions. We talked last section about the function and the function notation. We talked about inputs and outputs. And today we're going to specify those inputs as domains and those outputs as ranges. So let's go ahead and get started, and we will have a good time doing it. All right. So the first thing we need to really think about is what these inputs and these outputs are, and what you're actually doing when you input something into a function and receive something out of a function. And so we're going to look at these inputs as a set of inputs. And you'll notice the same set notation brackets that we had when we learned about set notation for set notation, set builder, interval notation when we talked about intervals and inequalities. You'll notice the same sets because we've got a set of inputs. Now the set of inputs could be every number in the world, or infinite numbers, or it could be one number, or it could be no numbers. You could have an empty set being your set of inputs. But the inputs that you put into a function are going to be the domain, and the set of outputs are going to be the range. Now, like we said before, this is that same interval notation, number line, inequality graph, so that you can really look at it and see, okay, so these domains and ranges are going to be reported as sets or intervals of numbers, unless there's just one. But for the most part, we're going to be reporting domains and ranges as intervals or sets of numbers, often in interval notation when the set has too many numbers. Like, how many numbers are there in between 1 and 2? There's an infinite amount of numbers, and so we need to report it as an interval from 1 to 2, and not 1, 1.1, 1.11, 1.111, and all of the numbers in between. So to start off, we're going to start real simple and say, here's a set of points. Let's find the domain. So you know how these, we talked about a long time ago, we've got x and y, we got x1, y1, maybe you could even go x2, y2, all the way through the end, labeling as many inputs as you have. If we're looking for the domain, which this first one's asking us for, we're just looking for the inputs. So what did they input to get the y's out? We're going to build another set, and we're going to write just a set of inputs where we're going to take just the x values. And that's it. So we're just going to write the x values, not in point notation or Cartesian coordinate notation. We're just going to write the input values and call that our domain. Likewise, you could probably find the range pretty fast if you took a different color highlighter and you said, we're going to find the range. You could probably do that on your own. And then you know, okay, well, when we have a finite amount or a finite set of numbers, it's pretty easy to report the domain and report the range. But what happens when you don't have a finite set? What happens when you have infinite numbers in the world? Well, this is where it's going to get really important to know 2 and then eventually 3 things later in the class. But this is where, when you see the word domain, your brain should immediately think. We say this in class, we call and response to this all the time because it's really important. When you see the word domain, I call them bad numbers. They're not mathematically called bad numbers. It's just a good way for you to see the word domain and think, domain, bad numbers. So a lot of times in class, we'll just say, domain, what should you be thinking? Bad numbers. But in math, we call these domain restrictions. And we've already talked about them in class a couple of times, but it's a really good thing to remind our brains of the 2 domain restrictions that we're really going to be looking for. And the domain restrictions we're looking for are any number in the world. So I'm going to write, sometimes I'll put a box and say any number that could go there. Sometimes I'll do x as a variable. Or you can just write a number sign, a number over 0. Any number, anything over 0 is bad, and we need to restrict that out of our domain. The second bad thing, right, for now, until we get later in class, once we get into logarithms and exponential functions, is a square root, right? And under that square root, you have to have a number bigger than 0, otherwise we're working in the imaginary world. And so these 2 things spit out 2 restrictions that we can impose. We can set the denominator better not be 0 or is not equal to 0. And that can find our first restriction. And in here we say the inside of the square root has to be greater than or equal to 0. And those are the 2 domain restrictions that we really have to imply before we look at anything. And so when I look at this function and I ask myself, is there any denominator? Is there any x on the bottom? Is it a rational function? It's not. And so we don't have to worry about the first domain restriction. Is there a square root? There's not. And so we get to report all real numbers, or all real numbers. Or if you want to do it in set notation or set builder notation, we could report it as x, where x is in the set of all real numbers. Or, and this is probably preferable, interval notation, where x is in between negative infinity and positive infinity, so every real number in the world. Those are 4 different ways you could write that. All of them are equally correct. They're just different ways to write all real numbers. And here we have our first domain restriction. So now we've got to say, hey, it asks us for the domain again. We think about those 2 bad numbers and say, what does domain mean? Domain restriction. So we need to restrict our domain. Do we have a square root? Nope. But we do have a number over 0. And so what we're going to do is we're going to set the denominator better not be or is not equal to 0. And that's where we're going to start to find our domain. So I'm going to take the denominator. I'm going to say that denominator cannot be 0. And then we're just going to solve the way we've already learned to solve linear functions. We're going to end up with 2x should not be or cannot be 1, which means that x cannot be 1 over 2. And from there, we have to do a little bit of thinking to apply this. I like to start with the number line because it helps us see it a little better. And you really only have to put that 1/2 there and say x can't be 1/2. Put a big open circle there. But you know what x can be? Everything in the world that's not 1/2. X is allowed to be. And so, because x can be everything in the world that's not 1/2, we start at negative infinity and we work our way all the way to 1/2. And then we unite that or union that with the set of numbers bigger than 1/2. And there we have a good interval notation. We have a good interval notation for what the domain restriction caused on our domain. Cool, not too bad. Nope, we have the other domain restriction. Might as well do all of them because it's important to see them all happen. We've got that same domain restriction. That's don't want any bad numbers, which means we don't want a negative number under the square root, right? That would be bad. And so we're going to take the inside. We're going to take the argument of the square root. We're going to say 5 plus 2x has to be greater than or equal to 0. And if you want a little side note, you could take that and say can't be negative. And we're gonna restrict our domain so that that can never happen. And this is why we learned about inequalities first, and this is why we learned about solving linear equations first, is so that we could apply it here. So now we've got x is bigger than or equal to, move that 5 over, divide by 2, and you end up with that. I'm going to skip the number line and go straight to interval notation so we can get some practice doing it. We obviously have that 5 over 2, negative 5 over 2, and we need to decide, do we want to go to the right or to the left? Is x bigger or smaller? And so because x is bigger than negative 5 over 2, we're going to infinity. And do we include it or we don't? Because we've got that underline, we are going to include negative 5 over 2. That falls directly out of the fact that you're allowed to take the square root of 0. You're just not allowed to take any negative square root. Okay, so there's the 2 types of domain restrictions that are really important. Let's see what else this section has for us. This is the same. Oh, we can combine multiple sets, which we've already done once with that first restriction, but let's go ahead and do it. In words, I'm going to do words last so we can see set builder first. In set builder notation, we've got a set of numbers, x, such that x has to be less than negative 5, right? X is less than negative 5. And because that's a closed circle right there, that's an inclusive circle, we're going to go ahead and add that line underneath it. But we've got another place that x could be. So we write an or. We say x has to be less than negative 5, or x could be in between negative 1 and 3, it looks like, with an inclusive at negative 1 and an open circle at 3. And then we can close up the set and say, there's set builder notation. X is either less than negative 5 or in between these 2 restrictions. Interval, like we said, is the most common one or the most important one. So we're going to start at negative infinity, work our way all the way up to negative 2, include it, and unite it with the set from negative 1 to 3. Awesome. All right. Now for the first time, we're going to talk about range. We're going to look at range because this specific example will show you that range is not always beginning and end. It's minimum and maximum, just like domain. Domain's not always beginning and end. though it worked itself out a little bit better because it's the independent variable. But what we're looking for is the minimums and the maximums on every case, not necessarily the last and the first spot. So for domain, you'll see what that means in a second. For domain, we look at the minimum, or the farthest left, or the smallest number. We can see that minimum for the domain is 1950. And these don't have dots. They should have some sort of dot. I know they don't. Let's go ahead and pretend like they gave us closed dots, because we need something. We need it to be open or closed. We don't know for sure if they don't give it to us. So we start at, on that red line, 1950. This is the domain. And we go all the way to 2000, it looks like. I'm going to draw that line just to check. Yeah, that looks good. And, oh, I drew solid dots. Because I drew solid dots, we include those two numbers. We are including those years in our calculation. And now for the range, it's going to look a little different because we're going to look at the minimum and the maximum. We're not going to look at beginning and end. If we looked at beginning and end, it'd look something like that, maybe 48. And it would look something like that, maybe 78. But we're not looking at the beginning and the end. We're looking at the maximum value, which looks like it's up there at 90. And so for the range, we're going to go from the minimum number that's on this graph, the minimum y value, which occurs at 1950 and is 48 or so. If you wrote 47, it's okay because they didn't give us that number. And then we're going to go up to 90 and include it because we drew solid dots. Awesome. Try it 7 is very similar to one we've already done. You can try that on your own. But we want to look at piecewise functions because these have a lot to do with domain and range. And so, on this piecewise function, just for the sake of including it in the class, I'm going to go ahead and draw a line right here. I'm going to draw an inclusive line right there. Even though it might not be in the textbook, I want to show you an example of what an inclusive line looks like as I was looking through this thing. This is just for practice. This is just for you to see what happens. We can talk about what happens if it's exclusive or it doesn't include it. We'll even draw that right before, but I want to, for the final thing, put that in there just so you can have an example of it. Okay, so we're going to look at this domain and this range. We're going to talk about a piecewise function, or 3 different functions that have 3 different domains that mash together to make one function because they'll pass the vertical line test. And so the first thing I'm going to do is look at where are these domains changing, or where is each function's domain. And so the first function's domain changes at -1. So I like to draw a straight up and down line at -1. I like to make it red. And I'm just going to draw at -1 a straight up and down line and say that's where something's going to happen. Something else cool looks like it's going to happen at 4. So I'm going to draw a straight up and down line at 4. I'm going to say those are some boundary conditions. Those are some cool conditions for this piecewise where it's going to change. And then I'm going to just graph my functions. It's each function in the section that it belongs. So this first section is the x is less than -1 section, not inclusive, and so we're going to graph that function. So maybe the first point I put in is -2. And I say, well, -2 is going to yield an answer of -8. Oh, that's already off the graph. That's way down here. If I plug in -2 into my function, so let's try that. F of -2, I'm going to get -2 cubed, which is -8. And so I plot the point, -2, -8. I'm going to go ahead and plot the point f of -1, even though it doesn't include it. And you'll see why in a second. F of -1 is probably -1 cubed, which is -1. And so we've got the point -1, -1. So I'm going to go over 1, down 1. And I'm going to draw a circle. But because that boundary condition was not inclusive, because there's an open circle there, I'm not going to draw a circle that's closed. I'm going to draw an open circle right there. And then connect my dots with a cubic function from that toolkit function section, from the last section in chapter 2 where I said these toolkit functions are really important. It's really important to see a cubic and recognize that looks like kind of like a snaky curve thing. And that makes a lot of sense because I've got the left side of the cubic function there. Now I'm going to look at this constant function, and if you look at that, that's a number. That's a constant function, which looks like a line. I'm going to write that. Cubic. This blue one's going to be constant. And that's a constant at -2. And so I'm going to start at -2, and I'm going to stay constant at -2 until I get to my next boundary condition. And there's graphing a constant function. Notice I put an inclusive or a dot there. That's because I added that thing, that the less than or equal to sign. If I wouldn't have put that less than or equal to sign, it wouldn't have been a dot, it would have been an open circle there. But because I wanted this function to be continue at every x value, I thought that might be a good idea. We'll see at 4 where we don't have a point at 4, because I'm not going to put 1 on 4. I'm not going to draw an underline on 4, and we'll see what happens when we graph the square root function. And so let's do a couple more plots, maybe f of, I don't know, 5. And what's the square root of 5? Oh my goodness, I don't know the square root of 5. Maybe 6, I don't know the square root of 6. Maybe we have to jump all the way to 9. Let's try f of 9, even though it's not on the graph. The square root of 9 is 3. And so if I go all the way over to 9, I'm going to go up 3. Well, I need another point then. So let's try f of 4. And f of 4 is the square root of 4, which is 2. So I can go over 4 and up 2. Oh, I went up 2 there. Whoops. 3. Over 4 up 2. But wait, that's a non-inclusive, or that's a less than sign, not less than or equal. So I'm going to put an open circle there. I'm going to connect my dots in the shape that, hopefully, if you've looked at those toolkit functions, you recognize that as the square root function. And the square root function looks a lot like this. And so we graphed a piecewise function. We graphed 3 sections of functions that all work together to make one piecewise function. All right, so this is the basics of domain and range. This is how domain and range work. You check for those 2 bad numbers, and then sometimes you use those intervals to graph functions below. Thank you for watching. I hope you have a good day. Don't forget to read through the textbook, try practice exercises, and try some practice problems before you work on your homework and eventually get to our Chapter 3 test. Best of luck in your studies, and I'll see you tomorrow.